Good morning, everybody. This is P.S. Racheti again, welcoming for our course Energy Engineering for final year mechanical engineering students. This is lecture number 2 and actually lecture number 8. Part B, you can say that introduction to steam power plant. Try to start with new. Just a minute. Prior to starting lecture number 8 or lecture number 2, you can say, on steam power plant, let us have some revision of the last class and then we'll proceed with today's lecture. Okay, so we have seen in the last class what is. So this is a part B. We have started general layout of modern power plant with different circuits. We have seen 4 circuits, and first of all we saw this. What is the steam power plant? A general layout of steam power plant. You have seen the 7 general layout plants consists of coal handling plant, ash handling plant, boiler plant. Then you can say this is a turbine plant, and so on. So based on this layout, we have seen what are the main parts in thermal power plant: coal handling plant, water treatment plant, DM water plant, boiler plant, and generator. So then we saw this criteria for site selection of thermal power plant. Any project you are taking in hand, you have to be ensure whatever the minimum requirements of that project. So the main 4 circuits we have seen: coal and ash circuit, air and gas circuit, feed water and steam circuit, cooling water circuit. So one by one we saw this coal and ash circuit, and in brief I am going to tell this because the next topic is also again fast and it takes more time. So this is coal and ash circuit. Then we saw air and gas circuit. These line diagrams are prepared by me based on the experience and based on the work carried out in thermal power plant. So you will not find in any of the books. So then we saw this feed water and steam circuit. And finally, we saw cooling water circuit, which cools the steam coming out of the turbine, and that condenses is reused in the boiler for generation of steam. So in cooling water circuit, we saw this hot scheduler pump, cold scheduler pump. Then this is particular main important part is cooling tower. Okay. Then advantages and disadvantages of steam power plant we saw. So then we stop here in lecture number or first lecture. So now today we are going to start with the lecture number 8 or lecture number 2 of steam power plant. It is important one and also little vast. I will try to explain at the easiest way. Try to understand. Okay, let us start. So as we know, the steam power plant is completely based on this Rankine cycle, which is again derived from the Carnot cycle. You have studied all this Rankine cycle, modified Rankine cycle, etc. With the base of the thermal power plant. So Rankine cycle or Rankine vapor cycle is the process widely used by power plants such as coal-fired power plants or nuclear reactors. In this mechanism, a fuel is used to produce heat within a boiler, converting water into steam, which expands through the steps in Rankine cycle as shown in figure 1, and the corresponding step in the pressure volume diagram. Pressure volume diagram, is not shown here. It is only temperature entropy diagram is shown here Then, so before that, just will again revise how the steam is being generated and converted into this mechanical energy and then electrical energy in the thermal power plant. So what are the components? So there are more four main components in the thermal power plant. There is the boiler, turbine, condenser, and pump. As you know, the water coming from the water treatment plant is being heated in the boiler, converted into steam, and being taken to the turbine for conversion of this heat energy of the steam into mechanical energy by means of rotation of the rotors, and that mechanical rotation is being converted into electrical energy with the help of a generator. Means work is done by the turbine. That's why it is work output, we can say, or work turbine. Just non keep in mind whatever I'm saying, these are coming several times and in numericals also. So this is the positive work output coming from the turbine. That's why it is termed as WT or plus W work. Okay. Then after exhaust of the steam from the turbine is being taken to the condenser where the heat is given out. That's why heat is dispatched from the device, that is condenser. So heat is out means here heat is negative, you can say here at condenser. Then this condensed water is being pumped back through the pump to the boiler. Here what is happening, pump is there, there is some external work, there is motor which rotates the pump or which gives the energy to the pump. Electrical energy converted into mechanical energy. That's why work is done on the system, and here you can say work is minus. So this work we can say WP or work pump. Okay, is by means of this pumping action the water is recirculated in the boiler for generation of steam. You will see here the heat is supplied in the form of combustion of coal in the furnace taking place. So the heat is supplied to the system, that is a plus. So you can say it is Q1, you say it is Q2 or Q condenser, which is minus Q1 or Q in. Here Q out, you can say. Just remind that. So in the Rankine cycle, now we'll explain this cycle in the Rankine diagram on TS plot. So 1 to 2, here you are seeing this 1 is there, 2, 1 to 2 is the pumping action, 2 to 3 is the heating action in the boiler from pressure 1 to 2, the pressure increased in the pump, and that second pressure will remain constant. 2 to 3, the pressure is constant, and at constant pressure the heat is added in the boiler, okay, and being superheated. So this is a saturated steam here at this point, and now this is the superheated steam. So then superheated steam is being expanded in the turbine by means of the process 3 to 4 here. So after the expansion, the condition of the steam is either wet, dry, or superheated. So just shown it is condensed, and then from 4 to 1 it is being condensed in the condenser. So this is the process, and again it is continued. So 1 to 2 work W pump in, 2 to 3 heat supplied Q in, 3 to 4 work output expansion, that is here shown W turbine output, and 4 to 1 heat is rejected, that is Q out. So if you remember this diagram and concept of this thermal power plant, you can easily solve the problems on the Rankine cycle. So what are the formulae used in Rankine cycle? Just before going to solve the numericals, this is a very important step, and I am telling this big in view of you have already studied the properties of steam and properties of steam and Rankine cycle problems. So I will just go through, and also you are knowing the values of this various enthalpies, entropies, temperature, pressures, etc. can be obtained from the steam table or Moliere diagram. Now here formula, what are the formulae used? So now I have told this is the just TS diagram here is in front of you. So work pump ideal is equal to H2 minus H1. Note that all the you can see energy conversions are being calculated in terms of change in enthalpy. Therefore, WP is equal to H2 minus H1. The process is 1 to 2, hence it is H2 minus H1. Or again, we know that V into P2 minus P1 by means of steady flow process or non-flow process we have seen in first law of thermodynamics. So V F1 at point 1, so volume can be obtained at pressure 1. This is the pressure 1 means 1 to 4. You are seeing this constant pressure line 1 4 and this is the second another pressure line that is 2 to 3, that is P2, P1 P2 we can say. So that is a P1 P2 is at higher side and P1 is at lower side. That's why you can write P low P high also. So V into P high minus P low is equal to P high minus P low upon 10. This 10 is the factor I will explain is taken to convert this into joules or kilojoules per kg. That's why it is divided after conversion. Okay, so this is 10. You can also write P1 minus P2 or P2 minus P1 also, so that no problem. While solving the problems, you have to convert that into either joules per kg or kilojoules per kg or joules or kilojoules. So here, why this is very volume is very small, hence it is neglected. And also you note that Vf1 is equal to Vf2. So taking this constant volume and Vf1 is neglected, then we see the formula for W pump is equal to P1 minus P2. P1 will be the higher side, P2 will be the lower side. Remember it. Similar fashion, Q in, heat is supplied in the boiler, is H3 minus H2. Q out is equal to H4 minus H1, where in the condenser heat is being rejected, 4 and 1. Okay, and turbine, now work output turbine is equal to H3 minus H4. So net work done is turbine output minus pump input. So therefore, that is also called as work shaft is equal to W turbine minus W pump. That is equal to H3 minus H4 minus H2 minus H1. Steam rate. So just remember this formula. No derivation is needed. Required for you. 3600 upon W net. Thermal efficiency is equal to W upon Q. W net upon Q supplied. Heat supplied. Okay. Rate of heat transfer, you just remember Q into mass flow rate, and power is equal to net work into mass flow rate. So numerical on simple Rankine cycle first we'll see. So what is the numerical? For the given steam cycle, the boiler outlet is equal to 10 bar, saturated, and condenser pressure is 1 bar. Find work done by the turbine in kilojoules per kg, work done on pump in kilojoules per kg. This is per kg. Heat supplied in kilojoules per kg and cycle efficiency. A very simple for problem is taken to understand and to brush up what you have studied in the last year's solution. Given data. So first thing you have to write whatever the given data is there. Then boiler pressure is given P1 10 bar, P2 is given 1 bar. And you know that you have to take these values pressure in either bars or kilopascals. Okay, then only you will get the values from the steam table. And steam condition is saturated, means the steam condition is on 0.1, means lying on this slope. Okay, now we have seen this line diagram again. Now here taken, so you can write these suffixes anywhere, 1 2 3 4. Accordingly, you have to write the formulae. Okay, so in earlier I have shown some different suffixes. Here it is different, no problem. It is with respect to this particular problem. You can write the suffixes from anywhere, but remember that the formula should be accordingly. So 1 to 2 is isentropic expansion in turbine. Okay, 1 to 2 here is 2 to 3 is constant pressure heat rejection in condenser. 3 to 4 pumping action is taking place, and 4 to 1 constant pressure heat addition in boiler 4 to 1. Okay, so Q1, here you can see WT, here it is Q2 and WP. Note the suffixes. At pressure P1, higher pressure. One more thing, whenever you are solving the problems on Rankine cycles, heat or Rankine heat cycle with reheat or Rankine cycle with regeneration or combination. So you must remember that first write down the given data, whatever the data is given, then you try to write the values of enthalpies at various points. That is, here you are seeing how many points? 1, 2, 3, 4. So at all these 3 points, if you are able to write the values of enthalpies, then it is easy to solve the problem. So here I'm showing here at P1, H1 is equal to 2778.1 kilojoules per kg, because we know the pressure at P1 means at the inlet of the turbine, and it is saturated. So at saturated, so for steam table or molecular diagram, you know the condition of the state can be defined by any 2 points, that is the parameters, pressure, volume, pressure, temperature, or is so like that, or the condition of the steam and the pressure, and so on. So if you know the 2 conditions of the steam, then you can find out the values from the steam table. So at P1, what is given? Saturation means on the line, slopey. So, and from the saturation table, you can steam table, you can see P1 and saturation condition. This H1, you can call it as Hg or Hs, is equal to 2778.1 kilojoules per kg. S1 is equal to 6.5865 kilojoules per kg Kelvin. So then you substitute, also you know that S2 is equal to S1. Now I'm not going in detail for that. As this expansion is taking place in the turbine is isentropic, then or adiabatic, you can say this S1 is equal to S2. Therefore, S2 is equal to S1 is equal to 6.5865 from the steam table. We have taken this value of S1 here. Then yes, but we don't know the condition after expansion of the steam in the condenser. Then to find the value condition of the steam at point 2, use this formula. S2 is equal to S1 is equal to SF plus X into SFG. At point 2, you can see just we use the suffix 2 here, and you can say S2 can be written as S3. Here you can say S3 means SF at point 3 plus X of SFG in between these 2 to 3. So this is a SFG, but the condition we don't know, that is a X, dryness fraction. This is the formula you have seen already in the last year or last year's classes. So SF plus X into SFG. So from that you will you know the value of SF from steam table at pressure 1.3026 plus X into X means the dryness fraction. This you can see 7.3594. That is the value SFG at point 2 with pressure P2. Okay. And minus 1.3026, that is a X. We have taken this X SF plus X into here it is taken the value of SG minus SF. Okay, so SG minus SF means what is this? This is the total SG at this point. This will be the SG, and if it will make it is SF, so part of this means into. So here it is the formula SG minus SF into bracket, that into X. You can find out the value of like this also. SFG can be written as SG minus SF. Okay. Therefore, the value of dryness fraction is 0.8724. Then we have to go for 0.2 H2. Where is this H2 is? So now we got the condition of the steam. So H2 is equal to HF, that is H3 from the steam table again, plus X into HFG. You can directly write down the values of HFG at pressure 2. It is like 2258. Then you will get the value of 87.3 kilojoules per kilo. Now we have found H1, H2. Now we are going to find out the value of H3. It is directly obtained from the steam table, 417.46 kilojoules per kg. And now H4, the H4 after pumping, it will be equal to H3. Means WP is equal to H4 minus H3. Therefore, H4 is equal to H3 plus WP. So now you know the value of H3. You know the value you know the value. So where we are, WP. So we have written the formula of WP. H4 is equal to H3. WP can also be written as VDP or equal to V into P2, P1 minus P2, higher pressure minus lower pressure. So V is equal to Vf at pressure, V equal to Vf at pressure 3. We find out from the steam table, which is equal to 1.043 into 10 raised to minus 5. Therefore, WP is equal to V. Actually, it is, you can neglect it's 1.043 into 10 raised to minus 5, but given okay into bracket the 1000 minus, now here it is taken in terms of kilopascals. 10 is converted into 1000, and this note this very important point here, or you have to convert from bar then later on to kilopascals, but here it is taken 10 bar to 1000 converted into 1000 kilopascals, and 1 bar is converted into 100 kilopascals. So this, if it is in kilopascals, then only you will get the value in kilojoules per kg. Very important step here. Therefore, now you obtain the value of WP. Substitute here in WP, you will get the value of H4. So H4 is equal to H3 plus WP is equal to so 417.46 plus 0.94 is equal to 418.4 kg kilojoules. Now you got the values of H1, H2, H3, H4. So remember always, and whenever you are solving the problems, write down the values of H1, H2, H3, 4 extra at the right side of the answer sheet, so that whenever these values are needed, and that can be taken from the right side of the paper. Okay. Therefore, WP is H4 is equal to, we got all the values. Now, W turbine is equal to H1 minus H2, that is the 390.8. Now you got all the values. WP, WT, Q, H1, H2, H3, 4. Therefore, heat supplied in the boiler is equal to, what will be the formula here? Here it is 0.4 and it is 1. H1 minus H4. H1 is on the higher side. So you will get the value of Q1. Therefore, efficiency is equal to W net upon Q1 is equal to WT minus WP upon Q1. That is 390.84. 8 minus 0.94. That is WP upon Q1 is 23. So you will get the efficiency 16.52%. Then steam rate is equal to 3600 upon W net. The formula I have given already. So W3600 upon 390.8 minus 0.94, you will get the value 9.234 kg per kilowatt hour. You just check the unit, how you got this. Moisture at the end of the turbine process. So after expansion, the what is the condition of the steam is 1 minus X, that is dryness fraction, means moisture content of moisture is X. So if you remove that one, that will get 1 minus 8724, that is the X value of X. You will get that it is a 0.1276 dry. So the moisture at the end of the turbine process is 12.76%.